Oh, hello and welcome. This is SFU Math 232. It's Brenda Davison. This is section 3.4, Subspaces and Linear Independence. Okay, so these are both big, important ideas. Sometimes that actually take a little bit of time to grasp. So at the end of this lecture, you want to certainly understand what does it mean to be linearly independent. Okay, so what we're going to do first is get a hold of the notion of closure, and closure refers to a given operation. So for example, if we say that something is closed, a set is closed under addition, it means that if we take any two vectors in S and then we add them together, we get a vector that's also in S. If that happens, then we say that the set S is closed under addition. So let's take a couple of examples. Here's a set, S1, has two vectors in it, 1, 0, 0, and 0, 1, 0. Is it closed under addition? So that would mean that I would, if I add any two vectors in S, that I would end up with a vector still in S1. I would end up with a vector still in S1. So let us just take an example here. I'll just add the two vectors that I have in my set together. I'll take that vector and I will add it to the other vector. And the result of that addition will be this vector here. And then I look at that one, and is that in S1? No, it is not one of the vectors in S1. There's two vectors in S1, and this one is not one of them. So this thing is not in S1. So S1 is not closed under addition. Okay, in some sense, you could think of this along the lines of, if I use the operation given, in this case addition, and I use the items in my set, I can escape outside of my set. That means it's not closed. Okay, let's take another example. Here's another a set. This is, okay, so maybe just let me pause momentarily and notice that this thing here is a finite set. It just has two vectors in it. This one here is an infinite set. It has all of the vectors of the form a, b, 0, where a, b are integers. And then we ask, is this closed under addition? So we can take any two, let me take any two vectors in S2, add them together, and see if I get something that is still in S2. So I'll just take some vector in S2. I don't know, let's take a vector here, A1, B1, 0. Of course, A1 and B1 are integers. And then let me take some other vector, A2, B2, and 0. And I'm going to add them together. And I'm going to get the following vector here, A1 plus A2. And then this one, this entry here will be B1 plus B2, and then this entry here will be 0. And then I'm ask myself, is this new vector here, is that in S2? And I look at the form of that vector, and it's some number. Let me just take these two together. It's some number. Let me just call that AN, maybe for new, and BN and 0. And AN and BN are both integers, so that fits the one of these vectors in S2. So S2 is closed under addition. So the answer here is yes, closed. Okay, I can't escape out. Like, so if I add together any two vectors here that have integer entries in their first two entries and 0, I add any two of them together, I always end up with a vector that still has integer entries on the first two thing, and in these first two dimensions, and 0 on the third dimension. So I can't escape, so it is closed. Okay, we have a similar idea, closed under this time scalar multiplication. Okay, so it's the same idea, but the closure, when we ask if something closed, we have to understand under what operation are we talking about. And so it's the same idea. It's closed under scalar multiplication if for every vector that you take and all C that are in R, that the vector formed is also in S. Okay, so let's again revisit S2. S2 is that definition right there. And we're asking, is it closed under scalar multiplication? And so I say no, it is not. Why? Because consider, as a counterexample, C equal to 3.6. And then if I take scalar multiplication of 3.6 times 1, 1, let's take this vector, 1, 0, 0. I get this one here, 3.600. And this thing is not in S2 because that entry is not a integer. So this is not in S2. So I've managed by doing this scalar multiplication to escape out of S2. So it's not closed under scalar multiplication. Okay, let's consider a new set, S3. These are all the vectors, the infinite supply of vectors, whose have a 0 in the third dimension, but the x and the y are real numbers. And then I ask, is this closed under scalar multiplication? And I say yes, because if I take any real number, some c like that, c in R, and I say c times x, that and I take c times y, this will be in R and this will be in R. I multiply two real numbers together, I get a real number. So I form a vector for which this vector here, for which these components here are in R, and that one is in S3 because S3 is all of the vectors that look like real number 0. So that this one is closed under scalar multiplication. So you could ask yourself, for the sets we're used to, for example, this is not for vectors, but this would be for the set of numbers. For the set of numbers Z, is it closed under addition? Is it closed under multiplication? So you consider taking any two numbers in the set Z and multiplying them. Do you continue to have an integer? And the answer is yes. If you take any two integers and you add them, do you end up with an integer? So and the answer is yes. And the set Z contains all of the integers. So this is closed under addition and multiplication. But for example, Z is not closed under division, because I can take two integers, say 2 and 3, and I can divide them and get 2/3. 2/3 is not an integer, so it's not closed under division. Whereas, for example, Q is closed under division. I take any two rational numbers and I divide them and I end up with another rational number. So that one is closed under division. So you can see there's a difference between Z and Q in terms of what operations they're closed under. Okay, that's the idea of closure. Subspaces. A subspace is a non-empty subset closed under addition and scalar multiplication. That's the definition. You need to be able to state this. If somebody asks you, is this a subspace? You have to think to yourself, okay, is it a subset? And is it closed under addition and scalar multiplication? You check those things. If you get two answers of yes, then you say it is a subspace. So the key things is that we need to have it to be a subset and that it is closed under addition and closed under scalar multiplication. So then here's the thing, question. We have a set, all of the vectors x, y, where x is greater than 0 and y is greater than 0. So let's just draw a picture. We're asking, is it a subspace of R2? So first let's just draw what R2 looks like. R2 is all of the vectors in here, right? So we could be thinking of any of the vectors going to like this, stopping at this point here, or stopping at this point here, like that. That's all of R2. And then we have a W. W is, and it's not including the axes. So W is here. So we're all of the vectors here, where x and y are both greater than 0. And we're asking, is W a subspace of R2? Now clearly W is a subset of R2. So let's just notice that. W is a subset of R2. Right? So this condition here is satisfied. Is it closed under addition? So we would next check that. W, so I'm asking this question, closed under addition. Okay, so I'm imagining taking any two vectors in W, this one say, and this one, and then when I add them together, so I'm taking here V1 and V2, and I add them together, so a picture of what that looks like. I get this here. I get V1 plus V2. Okay, is there any way that I can add vectors chosen from W and escape out of this first quadrant? I don't see how that could happen. So I would say, yes, W is closed under addition. So I answered this one in the affirmative. Then I check the next condition. Is W closed under scalar multiplication? Asking myself that question. And so I'm thinking, okay, if I take some vector, let me just do another color here. If I take some vector here, let's choose this one right here, V3. There, it's that vector V3. If I multiply it by any real number, do I stay here? And then I can see that if I take, for example, k equal to -1, and then I take the product k times V3, I get minus V3. Okay, so then that vector is here. There. That vector is there, and that is no longer in W. So by multiplying my vector V3 by -1, I've escaped out of W. So it's not closed under scalar multiplication. Therefore, it is not a subspace. So the answer to this question is no. Okay, so let's do a similar thing here. Is a line in Rn passing through the origin a subspace of Rn? Again, we're going to look in R2. I understand the question says here Rn, but let's look at R2 for some amount of intuition. That's I find this useful. So R2 for some intuition. Okay, so what we're saying is we've got R2, that R2 being the entire plane, and then we're looking at a line through the origin. So let's just pick some line through the origin, like that, and that line has we could consider all the vectors on this line, and then we would be asking if we take any two of those vectors, will we still stay on the line when we do that? So example, if I was going to take here V1 and then V2 is this longer one on the same line, do I end up staying on the line? If I multiply V1 or V2 by some number, 3, 10, 4.6, -8, do I stay on the same line? And I'm saying, yes, I do. We have here the idea that we're considering some vector, the line x. So this is the line x that is equal to t v1, where v1 is this. So I can capture all of the points on the line in this manner here, because it's going through the origin, x naught is 0. So this is all the points on the line. And then if I add, or if I add two of these together, or if I multiply by a scalar value, I don't escape. So for example, if I take x1 equal to t1 v1, and I take x2 equal to t2 v2, and I add those two together, I get x1 plus x2 that's going to be t1 plus t2 times v1. Okay, it's still on the same line. If I take x1 times some number k, that's going to be that will look like this: k times t1 v1, and then this thing is just some number, and then I see that that is still on the line. So yes, so the answer is to this one is yes. A line through the origin in Rn is a subspace of Rn. Okay, is a line passing through the point 0, 1, 0, 0 and parallel with the vector 0, 1, 1 a subspace of R3? Okay, so let us take a look at what this line looks like. This line passing through the point, here it is, here's a line. It's passing through the point 1, 0, 0, and it is parallel with the vector 0, 1, 1. So that's expression of all of the points on that line. Okay, so let's take a look at what can happen. That means that all of the vectors have to look like this. And so I could do the same kind of an idea. I can consider some value x1, which would look like this, 1, 0, 0, plus I'm putting t equal to 1, 0, 1, 1, and that would be this vector here. So this vector is on the line, x1 is on the line. Let us look at another vector on the line, x2. That vector is 1, 0, 0, plus, and I'm considering now t to be 2. So that would be then 0, 2, 2. And I would add this up, and I would get 1, 2, 2. Okay, and then I will add these two vectors together, x1 plus x2, and I will get this. When I add x1 plus x2, I get, so I'm adding, let me just make it really clear what I'm adding together. I am adding together this vector and this vector here. That gives me 2, 3, 4. Do that right? Hang on a sec. Here, I see what's wrong. This should have been a 1. Okay, so when I added these two together, I made a mistake. So this is 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 0 is 1. Sorry about that. Okay, so now I'm going to try to add them together. I get, I am adding together the vector x1. I'm going to fill it in. 1, 1, 1, plus the vector x2, which is 1, 2, 2. And I'm adding those together, and I get 2, 3, 3. Okay, now I'm asking, can I represent that? I'm thinking to myself, can I represent this sum? Can I represent that in the following way? Can I represent this like this? 1, 0, 0 plus t times 0, 1, 1. Okay, because that is what it has to look like if it's on the line. And I see what the problem is right away. I see, no, I can't. Because how am I going to get a 2 here? I cannot. I can put t to whatever value I want, but I cannot change this thing here from a 1 to a t to a 2 with any value of t. So this is not a subspace. Okay, I've taken two of them, I've added to them together, and then they're not on the line. So the answer here is no. Okay, and in fact, it is the case that every subspace must contain the 0 vector, and this one does not because of this problem here. Okay, so there's that problem, and then further we're just going to see, in fact, that of R3, the possible subspaces are lines through the origins and planes through the origin, the whole space, or the 0 vector. Okay, so in this, I just sort of answered this question here. The answer is the plane passing through the origin. That's key. Passing through the origin, a subspace of Rn. And the answer to that is yes. Okay, let us take a look at what a plane through the origin in Rn looks like. That looks like this. W, it's a set of all vectors x such that x is equal to It's going through the origin, so we don't have a constant term out there. It looks like this: T1 V1 plus T2 V2. Okay. That's what a plane through the origin looks like, and T1 and T2 are real numbers. Okay. Now, if I take any two things in there and I add them together, I get something that is of that same form. If I take this and I multiply it by a constant, I get something of the same form. So the answer here is yes. It's a subset and it's closed under addition and scalar multiplication. Yes, the set containing the 0 vector is a subspace. Yes. If I add 0 to itself, I keep getting 0. If I multiply 0 times some constant, I get 0, and 0 is in there, so I'm in. And the answer here too is yes. The whole space is a subspace. Okay, these two are less exciting. All right, so we call them the trivial subspaces of Rn. Okay. An important word. We're going to use this word all of the time, span. We actually, in fact, had a bit of a preview of this in one of the lectures 2 or 3 lectures ago. Basically, I'm going to give you a hand-waving thing about span, to maybe how to think about it. Span is you get some rules that some vectors you're allowed to use. You're allowed to, for example, let me just quickly give you an example. You get a couple of vectors. You get like this one, say, and this one, and you're allowed to walk along those vectors. And then the question of span is, if I'm allowed to walk along vectors like this, so I could go here, 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 here. I can take scalar multiples of them. I could go here, 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 like that. Can I move everywhere can I get everywhere? Or let me say, not can I get everywhere, but where can I get? And everywhere that I can get is the span. Okay, for example, though, if I was given two vectors like this, I was given this vector here and then this vector here, and I asked where can I go? I would only be able to stay along here. I wouldn't be able to escape out and get here by moving only in scalar multiples of this vector and scalar multiples of this vector and adding those things together. I would not be able to figure out, I would not be able to walk to here. Okay, so the span of these two vectors is this line, whereas the span of these two vectors here is the entire plane. Because that's what this is telling us. Okay, so let's get the formal definition here. If we have some number of vectors, S, the number of vectors here is S. Notice it does not have to be equal to n. So if you have some number of vectors in Rn, then the set of all linear combinations of these vectors is called the span of those vectors. So in this case, you can see what I'm meaning is by the span is all these linear combinations. It's where you can go using those vectors, and we don't denote that this way. The set of all vectors that are linear combinations of your given vectors is called the span. Okay, so if we are here, what is the set W equal to the span of the standard unit vectors in Rn? So that's the question. So again, we're just going to take a quick look at R2 because that sometimes is helpful. So let us take a look. W equals the span, and let's look at what the standard unit vectors in 2 dimensions are, and that looks like this: 1, 0, and 0, 1, like that. And we ask, okay, with those two vectors, where can we go? Making linear combinations of those, and where we can go is, this is equal to R2. Okay, we can get everywhere moving around like that. So we would say that the span of 1, 0, 0, 1 is R2. And it is true that if we have now, if we take this W to be the, let's call that W1 so we don't get confused, call this W2 as the span of E1, E2, dot, 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 En. Okay, so notice now this is n, and we ask where can we go with those standard unit vectors, then that is equal to Rn. Okay, so we now have a theorem. If we have S vectors in Rn, then the span of those is a subspace. Okay, we're going to prove that. I'm going to sort of wave my arms around actually to see why it's true rather than doing a traditional proof. Okay, I want you to see why this has to be the case. Okay, so not a formal proof. We have S vectors, that's these ones here. We have S vectors in Rn. Okay, I'm going to make another comment. If S is greater than or equal to n, then we have the possibility, it's not guaranteed, that W equals the span of W equal to the span of V1 to Vs, those are my vectors, is Rn. Okay, so we need to be able to span Rn, you need n vectors at least. Okay, it is the other possibility here is that the span of V1 through Vs is a subset of Rn. I sort of saw that in the example we just did. Okay, the span is a linear combination. So that's what the definition of the span is. So the span of V1 to Vs, that is the set of all vectors x such that x is a linear combination of the given vectors. And we have that T1 ... Those things are scalar real numbers. Okay, so we would then consider two vectors in the span of V1 through Vs. Let's consider vector x1. That vector looks like this. I'm going to call it T11 V1 plus T12 V2 plus ... plus T1s Vs. And then I'm going to take another vector, x2, and that's going to be T21 V1 plus T22 V2 plus ... plus T2s Vs. Okay, and what happens if I add those two things together? I take x1 plus x2, and I get this. I get T11 plus T21 V1 plus T12 plus T22 V2, etc. And I go all the way along, and then I have here T1s plus T2s times Vs. And I look at that, and I see that x1 plus x2 is a linear combination of V1 through Vs, because this right here is a linear combination of V1 through Vs. So that means that x1 plus x2 is in the span of V1 to Vs. Okay, so that means that if I take two vectors in the span of v1 through vs, and I take their sum, it is still in there. So it is closed under addition. And then I could also take k times x1. This one's even more obvious to see, I think. K times x1, I'm going to obviously get k times t11 v1 plus k times t12 v2 and plus dot 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 plus t times 1s vs, and that vector, this thing here, is a linear combination. Oh, I forgot the k here. Is a linear combination of the vectors v1 through vs. So the span of v1 through vs is closed under scalar multiplication. We showed it's closed under addition, and it is a subset. So we're done. It is a subspace. Okay. Let us look at what we're going to now call the solution space of a homogeneous. Homogeneous means that that zero is here. Okay, so we're going to look at the solution space of a homogeneous linear system. So here's our theorem. If AX equals 0 is a homogeneous linear system with n unknowns, then the solution set is a subspace of Rn. So we're thinking of all the vectors x which solve this linear system, and then we're saying that all of those vectors, if we take them all together, they are a subspace of Rn. They're clearly a subset of Rn, but we're actually imposing a more rigid condition and saying that actually when we collect them all up, we will get a subspace. So we have n unknowns, so that tells us the dimension of x. This is the of our solution vector. The dimension of x is n, because there's n unknowns. So we have a homogeneous linear system. So we can immediately say that, well, for a homogeneous linear system, the zero vector is clearly a solution. Okay, so that is a solution to this. Ax equals 0. X equals 0 is a solution to that. So the solution set is non-empty. There's at least one vector in there. So the solution set it's non-empty. Okay, if x equals 0 is the only solution, that's a possibility. We've seen that before, so that's a possibility. If that's the case, then the solution set is a subspace, because we just have the 0 vector, and the 0 vector is a subspace of Rn. So if this is our only solution, then we're basically done. The solution set is a subspace. Okay, how about if it's not? Otherwise, we'll proceed. Otherwise, we'll take any solution. So we have some other solution to this thing. We're going to call it x. I try to not to go like this. X naught. We'll take some other solution, x naught. So it's a solution. So that means that ax naught is equal to 0. And that, well, it's a solution. So that means that x naught is in our solution set. When we collected up all the solutions that we have to this equation into a set S. Now we're going to take any scalar. Okay, let us think what happens. We take so we're taking any scalar, and we want to show that the solution set is closed under scalar multiplication. So we're taking the scalar, and then we're imagining taking the matrix A, and we're taking k times x naught. So now we've taken our some solution that we know exists, and we are multiplying it by k, and then we're asking, does this satisfy the ax equals 0? So we do this. We're like, that satisfies K. We know we can move this because this is a scalar, and we've learned that we can move that out and write it this way. This is a legal situation. And we already know that this is equal to 0 because x naught is a solution. So this is equal to k times the 0 vector, and that is 0. 0 vector. You can think of it as, like, sometimes I just write 0, sometimes I write the 0 vector. You're thinking of the column vector filled with zeros. Okay, so that means that k times x naught is also a solution. It's in the solution set, and the solution set is closed under scalar multiplication. All right, so now let's take a second solution. Take a second solution. Let's call that guy x1. x1 is a solution, so it's in the solution set. And because it's a solution, we also have that a times x1 is 0. So now let us consider the sum of those two solutions. Here is the sum of these two solutions. Okay, I want to show that this is equal to 0, showing that x0 plus x1 is in the solution set. So I recall that I can distribute in this manner. And then we know that both of these things, x naught and x1 by themselves are solutions. So this is equal to 0 plus 0, and that is equal to 0. Okay, so that means that x naught plus x1 is in S, and that S is closed under addition. Okay, therefore S, the set of solutions, is a subspace. There we go. And because it's a subspace and it's a set of solutions, we call it the solution space. Okay, please take note that we started out here in the top with a homogeneous linear system. Okay. All right, so we got here the solution set is also called the solution space. So we've got that written out again. Drive home that point. The solution space of a homogeneous linear system is a span of some vectors. Okay. What do I want to say about this? Let me just say what I wanted to say here is if we are here in R2, what are the possible solution spaces? So we're still thinking like this of the homogeneous linear system. What are the possible solution spaces? Well, there is the possibility of the zero vector, the trivial solution only. There's the possibility of a line through the origin. Okay, that is the infinite number of solutions, a line through the origin, and there is the possibility of the entire vector space R2. Okay, so that is our possibility, and that each one of those is the span of some vectors. So we could, for example, have a matrix like this, 1, 2, 3, 4, and then we could have here x1 and x2, and that would be 0, 0. Okay, and then we have the possibility, well, in this case, I mean, excuse me, in this case, x, we're here, x is 0. So then we imagine changing these. Maybe we have, let me see if I can get one right away. 1, 0, 0, 0, x1, x2 equals 0, 0, like that. Then what happens? What are our solutions? We have a free variable, and we end up with the solution here being x equals to, let's see, t times, that'd be v1, and then this would be, this one is in fact 0. We have here, yeah, x1 is 0, and x2 can be anything. Okay, so we end up here with a line through the origin. That's a possibility. And then we have another type of a possibility like this. Why do we have like that? And there, the possibilities for x are both variables are free, and so we would have s times 1, 0 plus t times 0, 1, and the span of that is Rn. Okay, so it's a span of some vectors. We've got here this possibility, and this possibility. Okay, is every subspace of Rn a sum of some vectors? The answer here is yes. Okay. Continuing along, we have got another theorem. A lot of theorems in this section, I will confess. We're sort of laying the groundwork so that we can do a bunch of things. So there is a large number of theorems and proofs in this lecture, which does make it actually a bit slow going. You may want to, listen to part of this, a few of the theorems, go through the proof, think about it a bit, and then come back and continue, because it is hard to absorb a lot of theorem proof things in one longer kind of marathon. You maybe want to do a few sprints instead. Okay, so let us just say we've got an m by n matrix, and then we are considering what is this solution space of this guy, and it is all of Rn if and only if all of the entries in A are 0. I mean, we basically just saw an example of this just at the bottom when I used that 0, 0, 0, 0 matrix. Okay, so that is part A. And part B of our theorem is if we've got two m by n matrix and they are equal if and only if ax equals bx for all x in Rn. Okay, so we want to just prove these two statements. Do I want to say something just to clarify? Let me just maybe add a word of clarification of what part A means. I'm not starting the proof yet. So ax equals 0 for all x in Rn means that we take any vector x in Rn and ax equals 0. Okay, that can only happen. This is what we're going to prove. That can only happen when A is the 0 matrix. So it would be in a R2. This would be, we would have A looking like this, and we're saying no matter what we choose, no matter what we choose for x1 and x2, we're allowed to choose absolutely anything, and this thing will always be 0. And what we want to show is if that's the case, then A has to be equal to B and equal to C. And they all have to be 0. Otherwise, that can't happen. We would be able to find some x1 and x2 that it did not come out to 0 unless all of these things are 0. Okay. So we'll do. We will do the proof of here now of part A. So we're going to do part A, and it's an if and only if proof. Again, if and only if, which means we have to show it in both directions. So we'll start out with A, and we're going to go in this direction, and we're going to assume that A is consisting of all zeros. Okay, so now what we want to show is that the solution space of AX equals 0 is all of Rn. Okay, so then this is not going to be difficult. Then, I mean, we assume that the A is 0, and then that means that AX is equal to 0 for all X in Rn. Okay, because I'm multiplying by 0. I mean, A is 0, so no matter what X I give, I get 0. Therefore, all values of X work. Therefore, the solution space is all of Rn. Okay, that's in one direction. And then in the other direction, it's a little bit more complicated. We assume that AX equals 0 has a solution space all of Rn. We make that assumption. And then let us look at this. A is equal to A times I. So I'm just going to multiply. This is a true statement. And because I is the identity matrix, and I'm thinking of I like this. It is a collection of column vectors, which are the unit standard unit vectors. Okay, so for example, I2 is 1, 0, 0, 1, and if I draw this here like that, I'm thinking that, oh, I see that it is a collection of E1, which is 1, 0, and E2, which is 0, 1, and those are the standard unit vectors for R2. So that's how I'm thinking of I in that way. Now I'm going to multiply A times I. A times I then can be thought of like this. A times E1, that'll be the first column. A times E2, second column. A times En, third column. Okay, let us just again, normally, I mean, in a proof, you're not obliged to run an example down the side and sort of see what's happening. But this is, yeah, I'm not writing a textbook here, right? I'm trying to get you to understand how the proof is working. So let us just make sure that we feel happy about that. Let's just look at a nice, easy example. Here, let's take A to be one of my obviously all-time favorite matrices here. And then look what happens when we take A times I. Well, that is, I mean, A is equal to A times I anyway, so I can just add that here. There it is. Okay, and then I'm claiming here that looks like this. 1, 2, 3, 4 multiplied by 1, 0. And then the second column is going to be 1, 2, 3, 4 multiplied by 0, 1. And that, I'm going to actually perform this multiplication, and I'm going to get here 1, 2 times that is going to give me 1, and that's going to give me 3, and then I'm going to get 2, 4. Okay, these vertical bars are just separating my columns, and I see that that is A. So A times I is equal to this thing here, and that is equal to this guy. So I've justified this a little bit with this example here. Okay. Okay. So A times E1, that's A times a vector. And the solution space of AX is all of Rn. So therefore, the solution space includes E1. Does that make sense? So we know the solution space is all of Rn. That means that means the solution space is all of Rn. That means that Ax equals 0 for no matter what x I put here. So now I'm saying I've got here A times E1, and E1 is a vector in Rn, so this means that this is, well, I'm going to put this on here. So that means that that is equal to 0. That means A times I, which is AI is then equal to like this, 0, 0, because that same logic applies for all of them, 0. And then I've shown that A, which is, this is equal to A, because A times I is A. So I've showed that A has to be 0. Okay, so that is the other direction. So now we have part A proved. We're going to move on to part B. This is straightforward. So what are we trying to show? We've got, we're trying to show A equals B if and only if AX equals BX for all X in Rn. So we do the two directions again. We assume A equals B, and then we simply multiply both sides by X. And that's the end of that. Okay. Now we assume AX equals to BX for all X in Rn. And what happens then? We go like this: AX minus BX equals to 0, and that implies that I can, let's just go like this: A minus B times X is equal to 0, and then that means that A minus B is equal to 0 by part A, and therefore A equals B. And we're done. Okay, so that is in our book, theorem 3.4.4. So what we're going to do is, when we start to solve problems, what we're going to do is we're going to be using these theorems. And I think if you take the time to go through the proofs and really understand why these are true, then it'll be much, much easier for you to see when you make one statement and you're like, oh, because of that, then this and this and this and this and that, and then you're finished. And what you're doing is using these theorems in clever ways. Okay, our next important concept is linear independence. Suppose we have two vectors and they're in R3, and then we look at the set, which is the span of those two vectors. So we're just going to talk a little bit about what that looks like. The set W looks for different vectors V1 and V2 in R3. Okay, so let us consider, for example, V1 equals 1, 0, 0, and V2 to be equal to 0, 1, 0. Okay, I've got two vectors in R3. What does that look like? So let me just draw you a picture of what that looks like. I will draw the axes in this manner here. So I have here the x-axis, the y-axis, and the z-axis. And my first vector V1 is sitting right here. This is V1. Okay, V1. And then where is V2? That is right here. Okay, and then I'm asking where is W, and I'm saying then this here W is, and it continues here, but it's the ground, if you will. It's the entire XY plane. So in this case, W for these two vectors, W equaling the span here of 1, 0, 0 and 0, 1, 0. That is, W is the XY plane. Okay, we could do another example. Just change the color so we don't get any confusion here. So let's just do another example. What if I were to take these two vectors here? I'm going to do the same exact axes. I'm going to have here X, Y, and Z. And then I'm going to take two vectors. I'm going to take V1 here on the W axis. So that's going to be V1. So what does that look like? Well, it looks like just what it looked like before. It's V1 is 0, 1, 0. And then I'm going to take V2 here instead. So V2 will be along the Z axis. So V2 will look like this, 0, 0, 1. Okay, and then what is the span? So that here is this plane here along the, I don't know, along the back wall, if you want to think of it that way. So we've sort of the floor and then the back wall and then the wall sticking out into the room. Okay, so let's try to visualize what's happening here. And so that in this case, the span of these two vectors here is the YZ plane. Okay, so that is, I guess, two examples. We have to now, however, look at what would happen, as an example, if we were to, I'll just do this one a little bit higher. What would happen if we were to take two vectors along the same axis? You get a sense of how that will be different. Okay, so if we were here, x, y, and z, and then we took two vectors, let's just put them both on the x-axis, like that, v1, and then another one, v2. There they are. And then we look at the span of that. Then in that case, you're making all the linear combinations of v1 and v2, and you're only able to move back and forth along the x-axis. So in this case, the span of v1 and v2, which we've been calling w, is equal to the x-axis. Okay, so is possible if you have one vector. Okay, the maximum possible thing you can span with one vector is a line. The maximum possible thing you can span with your two vectors is a plane. However, it is possible for two vectors to only be able to span a line. And then if you have three vectors, you have the potential of spanning all of R3. Okay, so that's going to be important. And it's like, how do you know, given your vectors, how do you know which category you're falling into? I mean, it's possible to have three vectors all along one line and only be able to span the line and not a plane or the whole space. Okay, so we're going to try to be answering these kind of questions. So we need this idea of linearly independent, which basically means you cannot make any one of the vectors out of combinations of the other ones. Okay, so let's get that formal definition. The linear independence. A non-empty set of vectors in Rn is linearly independent if the only scalars that satisfy this equation are all zeros. If they're not all zeros, then we call those vectors linearly dependent. Okay, it means you can't make it. This linear independence means that you cannot make, for example, let us just say, it means you can't make any one of these out of a combination of the others. So for example, what this is telling you is I cannot take V1 and make it in this way. Something V2 plus something V3 plus dot 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 plus something DK. That can't happen. I won't be able to do that. So I can't, they are independent in the way that you cannot make one from a linear combination of the others. Okay, so let's investigate, are the following sets linearly independent? So I'm basically asking, can I out of making linear combinations of this one, can I get this one? The answer is no, I cannot. What I'm asking is there then, so I can rephrase this. Does there exist C1 and C2 such that this equation will be true and not both C1 and C2 will be 0? So let's see what happens. We can just write this out, see what the solution set of this this system is. That looks like this. C1 plus 0 will have to be 0. That means that C1 will have to be 0. And also the second equation is telling me that 0 plus 0 is 0. That's fine. The third equation is telling me 0 plus C2 will have to be 0. That tells me that C2 is equal to 0. So there's no possibility that I can add up combinations of this one and get this, unless this is 0 and this is 0. So the question here is, the answer here is yes, S is linearly independent. Okay, let's look at the other type of an example. Can I make this one out of this one? Yes, I can. I can see this actually, but I'll do it a little bit more formally because I can see that this one, the second one here, is 3 times this one. So this one I can make out of a scalar multiple of that one. So these things are linearly dependent. So let's see, let's write the same thing of equations. So I could go here C1. I'm wondering, can I find C1 and C2 both not 0 so that this is true? Same question I asked before. And I see from the first equation here that 0 plus 0 is 0. That doesn't get me anywhere. Oh, now I see that C1 plus 3C2 has to be 0, and 0 plus 0 has to be 0. So easily I can see that I could, for example, take C1 equal to 3 and C2 equal to -1. Okay, and then when I added that together, when I put that value in here, let me just put it in. Yeah. I'm going to say now, I'm going to take C1, I'm going to put it to 3, and I'm going to take C2 and put it to -1. And I see that this equation is satisfied under those circumstances, and that C1 and C2 are not 0. And at least one of them is not 0 is all I really need. So therefore, this second set S here in part B is linearly dependent. So it is not linearly independent. Okay, how about if you just got one vector? Is it linearly dependent? Yes. Okay. What happens if you've got 2 vectors and the 0 vector? Is it linearly independent? No. Okay, this is a problem. Okay, how do I see that instantly? Well, I'm wondering the same exact thing I always am. Can I find constants C1, C1, C2, and C3 so that I can add this thing up to 0 and all the constants are not 0? So here I'm going to write that. I'm going to be saying to myself, can I do this? C1 times U. I'm going to write it like that. C1 times U plus C2 times V plus C3 times 0. Can I make that equal to 0 when C1, C2, and C3 are not all 0? And yes, I can, because I could just take C1 equal to 0, C2 equal to 0, but I could, for example, take C3 equal to 1. These are not all 0. Therefore, the set is not linearly independent. Okay, let's keep going. We have a set S with 2 or more vectors in Rn, and we're claiming that it's linearly independent if and only if at least one of the vectors is expressible as a linear combination of the other vectors. I mean, this is really very straightforward. In fact, it's sort of, I posed this way just a little bit. So let us just do this quickly. So we do it both ways again. We assume S linearly dependent. Okay, what does that mean? That means when we take a linear combination of all the vectors, it will be equal to 0 where C1, C2, etc. are not all 0. Okay, so let's just suppose, and we can pick any one of them. So we know at least one of them is not 0. Let's just suppose it's C1. If it's not, just change it to whichever is not 0. So suppose C1 not 0. Then I can express V1 like this: 1 over C1 minus C2 V2, etc. So your basic algebra. Okay, so there's V1 expressed as a linear combination of the other ones. We've done it one way, so let's go the other way. Assume a vector in S is expressible as a linear combination of the others. Okay, let's just write down what that means. That means, for example, V1 is expressible as a linear combination. Let me just, because I know I'm going to flub this, I'm just going to call this C2, C3. Otherwise, I'm never going to be able to do this. V3 plus dot 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 plus Cn Vn. Okay, so I'm saying, okay, assuming there's some vector like that, then I just move everything to the other side. And that is equal to 0. And we have that C1 is equal to 1. Right, there it is. C1 is equal to 1. That's not 0. So we have we have taken all linear combinations of the vectors in the set, and we've been able to make it equal to 0 when one of them, at least, is not 0. So this is basically then C1 to Cn, not all 0, because C1 is not 0. Okay, so it's not all 0, therefore S is linearly dependent. Okay, it's a little bit like if I have, say, 2 linearly independent vectors, and I add a third one. Do I get any more ability to move around? Do I get any more information? And if the third one that I add is just a combination of the other two, I don't really get anything. But if I can't make that third one out of a combination of the other two, then I sort of have a new tool. I can move somewhere where I could not move before. Okay, so here's a corollary of this. 2 vectors are linearly independent if and only if they're parallel, and 3 vectors are linearly dependent. Did I say independent? I'm going to read it again just in case I accidentally did. These 2 vectors are linearly dependent if and only if they're parallel, and that's for the 2 vectors. And if we have 3 vectors, they are linearly dependent if and only if they lie in the same plane. Okay, basically in this case, you can only move around in a line with those vectors, and in this case, you can only move around on a plane. You can't get all of R3. You can only move on the plane, and in this case here, you can't get all of R2. You're stuck on your line. Okay, how do we check for linear independence? So we have a theorem. We don't check well, actually we will check using the theorem. So, but we first have to prove that the theorem is true so that we can use it with confidence. So we've got a homogeneous linear system, and we're saying that it has only the trivial solution if and only if the columns of A are linearly independent. Okay, so we want to prove this in this if and only if, so we got to do both directions again. So we'll go first in this direction, and we'll assume that the columns are linearly independent. Assume the columns of A are linearly independent. So we're considering that vector A as a collection of column vectors. Assume the columns of A are linearly independent. Okay, so I'm going to represent A then as that matrix of linearly independent vectors. There it is. Okay. I'm using that bar there to just sort of separate the columns and say I'm considering A. It is a matrix, and I'm looking at it as a collection of column vectors. We're assuming that those vectors are linearly independent. So we would have that C1 times V1 plus C2 times V2 plus dot 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 plus Cn times Vn equals 0. If we had that, that would imply that C1 to Cn all 0, because that's what it means to be linearly independent. Okay, so now we consider the homogeneous linear system AX equals 0. And what we want to show is that the only solution to this is x equals 0. Okay, so let us just, I mean, really, this is a matter of just, well, one way of doing this anyways is just to really just go through from the first principles and just ensure it is true. So I'm taking A, there it is, and I am multiplying through by my a solution vector, and that is supposed to come out to be 0, and I'm going to try to, what I want to show is like all of these numbers have to be 0. Okay, so I could simply rewrite these vectors like this. I could write like this: v11, v12, dot 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 in their component form here, like that. So I can sort of perform, not so I can sort of, so I can perform the multiplication and see what's happening. I'm going to actually perform this multiplication. Okay, so let's just go ahead and do that. What does that look like? It looks like this: v11. So I'm taking this, like always, multiplying a matrix times a vector, that first row into the first column, and I get this. Okay, and I do that for all of them. Sorry, I was right in the first place. I am multiplying. No, I was right in this. Like that. Okay, yeah, I'm taking the first row into the first column. Then I'm going to take the second row into the second column. Okay, and I keep going, and I do that for all of them. Except, I got this in the back. This should be 1, 2. 1, 2. This would be the second one here into there. That is 1, 2, and that would be n2. Okay, n1, n2. Okay, and then yeah, let me do the last one. So now I'm considering taking this one, multiplying it by the x. I get v1n x1 plus v2n x2, and I keep going. vn n xn is 0. Okay, so how could I rewrite that? x1 times v1 plus x2 times v2 plus dot 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 plus xn times vn is equal to 0. Huh? But these are just things, and we know that in this case, because of the linear independence, those things all have to be 0. So this implies that xi, the xi's are all 0. That's only the trivial solution. So one direction is done. Okay, and then the other way is straightforward, only the trivial solution. So that means ax equals 0, implying that x is equal to 0. And ax, as we've just shown above, looks like this: x1 v1 like that, plus x2 v2 like that, the whole way, xn vn, and that is equal to 0. We know that it's equal to 0 only when x1 equals x2, etc., equals xn equals 0, because only the trivial solution exists. That's our assumption going this way. Only the trivial solution exists. So this only happens when all these things are 0. And that means that because there are then no other constants that we could make this equal to 0, that is our definition of what is linear independence. So therefore, v1, etc., vn are linearly independent. And that's the columns of A. So then the columns of A are linearly independent. Okay, let's see how we can use this now that we're convinced that it's true. Or maybe even better, say convinced that it's true. Maybe we better understand why it is true. That's really the purpose of the proof. Okay, so are these vectors linearly independent? Okay, so what we can do is we can set take these vectors, put them into the columns of a matrix. Okay, that is that I've got three vectors. I put them into the three columns, and I'm wondering, I could check then, does this solution have only the trivial solution? Then I can use the theorem to draw the conclusion that these vectors are linearly independent. Okay, so now I've done this, and now what I want to do is check the solution, and I want to see, is it the trivial one or not, or are there more solutions? So I put this guy into the augmented matrix like this, like that. Okay, I do my row operations, and I'm just going to do one row operation before stopping, and that's going to be this one. I'm going to switch the, okay, I'm stopping right here, and I see this problem right here. It's not a problem, but I see this, which tells me what? That I have a free variable. So I see that here x3 is free. Therefore, there is more than one solution. Okay, so it's not just the trivial solution. So then I'm done. So therefore, they're linearly dependent. And then that means that I must be able to make one of them out of some combination of the other two. So let me just see how I can maybe look and just see how I could do that. Let me just think, okay, hang on, doing this on the fly here. So I think that I should be able to make one out of a linear combination of the other two. So can I do that? I'm going to take 2, 0, 2, and that is going to be equal to 1 times 1, 0, 1 plus 0 times, yep. So I can make this vector out of this combination of these two. They are linearly dependent. Okay, we are nearly done here. Long lecture. I've gone kind of slowly and hoping that this does take some time and thinking about it. So I definitely have taken more than the 50 minutes. Okay, so let's just observe something. One is that if you've got more than n vectors in Rn, then at least one of them will be combinations of the other ones. Okay, so it'll be linearly dependent. And now we can expand our ever-increasing list of things that are equivalent. Any one of these statements are equivalent to the other ones. So we had already proved before, quite a long time ago, we'd already proved these ones. We just did this one, okay, on the previous slide. And so the only remaining thing here is this guy here, H, and that is really easy to show. You could take a look at page 131 on our BuzzFeed textbook. But let me just wave my arms around and tell you what the idea, to show that G implies H and H implies G, well, we could this one, we know this one, we just showed that this one here, the column vectors are linearly independent, shows that the matrix is invertible. So where is it? Sorry, I pointed to the wrong one. Let me just bend my arrow up. That implies that, right? So the matrix is invertible, and then that means matrix is invertible. We saw earlier, if and only if its transpose is invertible. Okay, that's the key insight here, because that turns the column vectors into row vectors, and then and then so that means the column vectors of A were linearly independent. Then those are the same vectors, the row vectors of the transpose. Okay, so we're done. So that's the basic insight there. You could flesh out the details there yourself, or you can take a look at the Busby text on that. Okay, lots to absorb here, and we are done, and we'll be back with the next section. Thanks, guys. Bye.